So welcome to this lecture. This is the second lecture about physics-informed neural networks. So Sid last week talked about the importance of partial differential equations and how they're important for kind of every scientific domain that we want to study. And then he showed you a really exciting kind of new technique that's happening, which is called physics-informed machine learning. Physics-informed neural networks. And we use neural networks to learn solutions to those differential equations. So in this lecture, I'm going to give you a quick recap on what physics-informed neural networks are, recapping everything that we covered last lecture. And then I'm going to tell you more about the details of how we actually train PINNs. And also, hopefully, I'm going to do some live coding and code a PINN in front of you and show you how we actually do it in a modern framework. In particular, PyTorch. And then I'm going to talk about some of the really nice applications that we can use physics-informed neural networks for. And I'm going to hopefully show you that as well as simulation, we can also use PINNs for inverse problems and equation discovery as well. So they're very versatile technique. Okay, let's have a look at the timeline again as well. So yeah, we're on the second lecture of PINNs. We also have one more lecture, which I'm going to give next week, where we're going to really talk about the limitations of PINNs and also their extensions as well, and really get to the kind of forefront of the research in this area. Okay. Okay, so let's step back a little bit, and I really want to start from basics, and I also want to try and motivate PINNs from a more machine learning perspective. So I know last week, Sid motivated them from a scientific partial differential equation perspective. This is the real benefit of studying, deep learning in scientific computing is we're really at the intersection, and it's really valuable to look from a machine learning perspective as well as from a traditional scientific perspective. So how do PINNs work from an ML perspective? So let's just go back to, remember I was teaching you all about the basics of machine learning. And we have, these neural networks, and one of the most popular tasks is to do regression. So we have a bunch of training points, and we want to try and fit a neural network to those points. And we have all these architectures I was describing before: fully connected, CNNs, ResNets, et cetera, et cetera. And the most common loss function for these regression tasks is a mean squared error. So imagine that I've got some points. We're going to say it's from some scientific process, but we don't know anything about that process. And one of the key tasks we really want to do is fit a model to those points. And so we could train a neural network to do that, right? We just take our training points. These are these orange dots, and we're just going to fit a very basic, fully connected network to those points, using a mean squared loss. And what you can see is exactly what I was telling you about in the basics of ML is neural networks within their training data really, really nicely fit that solution of that data. But outside of the data, it doesn't generalize. Even though it's very clear in the training data that we've got some kind of oscillatory process going on. Okay, so how do we improve on this? So what if I told you that these points are actually from measurements of a damped harmonic oscillator? So this is a really classic problem in physics. It's a mass on a spring with some friction to dampen the oscillations through time. And so this is the real difference when we're using deep learning in science compared to kind of pure machine learning, is we have this kind of vast understanding of prior knowledge of physics and science. So we really want to put that into our machine learning. And so the particular thing that we know is, when we know this is the underlying thing here is a partial differential equation, or in fact, an ordinary differential equation for this 1D case. So we know that the displacement of this mass as a function of time just depends on its derivatives, and then the mass of the spring constant, and the coefficient of friction. So K here is the spring constant, mu is the coefficient of friction, M is the mass. Okay, so PINNs are a really simple idea, really, really simple. And the whole idea is we're just going to add one extra term to the loss function, which makes sure that the underlying physics is obeyed. and more precisely, the underlying differential equation itself is obeyed. So how does this work exactly? So remember that we have a neural network here that's given a time point t, and its output is a prediction of the displacement. So what it's actually doing is it's making a functional approximation of the solution to the differential equation. So neural network here approximates u here, which is the solution of our differential equation. Okay, so, and we had these points, these training points, and we had the mean square loss. And so what the PINN just does is add this extra loss term here, which says, okay, as well as fitting to the data, I also want to make sure that at some points in the domain, actually many points in the domain, I'm going to take derivatives of my neural network and collect those derivatives together to form this differential equation, or the residual of the differential equation. So you can see here, if the neural network fits the differential equation, then this term's going to be 0. And so that's going to minimize that physics loss term. And so what we need to do to evaluate this is to have these points here, random points in the domain. We call them co-location points. And they're just the green points here. So this is the extra kind of data that we add. And then if you train the network using this extra loss term, you can see if we have green points spanning for much longer time points, we start to fit the actual true solution of the PDE much better. Okay. So yeah, we have two names for these different terms. We would call this, in machine learning speak, this is just a supervised loss term, standard mean squared error. And in what we add is this extra physics loss based on our PDE. Yeah, and Sid introduced this as the PDE residual, or I'm going to call it the physics loss from now on. Okay, so from an ML perspective, well, the physics loss is actually an unsupervised regularizer. So remember, yeah, sorry, I missed it. Yeah.
I was just wondering about the physics loss. We have the parameters m, u, and k.
Yeah.
So how do we treat these? Do we treat these as hyperparameters? Or?
Yeah, exactly. Right. So we're going to get onto this, and especially when we talk about pins. At the moment, I'm just assuming the mass k and mu are just fixed. We know that, so we know the full differential equation. And in that case, the PINN is just learning the solution. But we're gonna change that, and we're gonna see how that allows us to do inverse problems and learn those as well. Okay. But yeah, from a machine learning perspective, the physics loss is just an unsupervised regularizer. So what does that mean? So what is a regularizer? Can anyone remember from the second deep learning lecture? What's the purpose of regularization?
Make the norm of the weights small.
Yes, exactly. Well, that's one type of regularization. So, but what's the general purpose of regularization? Yeah.
And to avoid overfits.
Yeah, exactly. So remember, if you have like a really expressive neural network, then the network that optimizes the empirical loss on your training data might be really far away from the true function that you want to measure. And so regularization tries to add priors or a preference on that function space to make it closer to what we think the true function is. So it's the same here. Like we think the solution is oscillatory, and we know the PDE enforces oscillatory solutions. So we're preferring the function to be oscillatory. That's how we can interpret PINN from machine learning speak. So why is it unsupervised? Anyone know?
Because we actually don't need to calculate the supervised. We just do, like, we just take a sample from the domain.
Yeah.
And then we just calculate the PDE residue and just train this.
Exactly. Yeah, perfect. So it's unsupervised because we don't need any labels. So in the supervised part, we had to have labels of the solution. Unsupervised here, we just need coordinates in our domain. So this is great. This means we can rely less on the data term, and we can actually just train in an unsupervised fashion. So yeah, that's really, really useful. Okay, from let's switch to the mathematical perspective that Sid was talking about last week. So we can see very clearly that PINN is providing a way to solve this differential equation. And so what is happening is the neural network is a functional approximation of the PDE solution. So this is really important, that the neural network itself is a function, It's not like, so if you think about finite difference simulation, when we solve the simulation, we end up with like a vector or a matrix, like a discretized solution, a bunch of values. This is not what we're getting when we train a PINN. What we get is an actual function that we can query. We can query the neural network here at any point in the domain. So that's really cool. We call that mesh free. And it's this kind of difference between continuous kind of simulation and discrete simulation is very interesting. And you can go really far into like research into understanding the differences between those. Yeah, so it's a functional approximation. And then the physics loss here is, like I said, it's making sure the neural network satisfies the PDE. And then from a mathematical perspective, well, we actually need two things when we're simulating PDEs. We need the PDE itself. We also need to assert boundary conditions, like boundary and initial conditions. And the reason for that is we want to make sure we learn a unique solution and not like a random particular solution to the PDE. Yeah, so if you think about integrating PDEs, you have like integration constants. You want to figure out what that constant is. You need a boundary condition for it. So in this sense, that's what the supervised loss is doing. It's providing a boundary condition. And in particular for this PDE, it's saying, okay, the mass starts at this point here and it has a velocity of 0. So that's what we're saying implicitly by having all these training points. Does that make sense to everyone? Nice. Okay. It's really important to get this. This is the kind of core principle of PINNs, and everything else in the next lecture and so on is just going to be extending this idea. Okay. Yeah, so we can abstract this a little bit. I showed a PINN there for the damped harmonic oscillator, but what's really powerful about PINNs and why they've been so popular recently is because they're actually a general framework, and so it's very easy to see we don't have to use a damped harmonic oscillator PDE. We can just use any PDE, and then the PINN becomes a general framework for solving kind of any differential equation within limits, I guess. And so how do we abstract this? Well, okay, so this is just PINNs for solving PDEs, so the basic case. And so we say, okay, we have this kind of differential equation, and how do we write it? We just say, okay, we have the solution to the differential equation here, which is u of x. X here could also contain, it's a vector, so it could also contain time. I've just bunched it all into one letter. And then we have some differential operator that we apply to u, and then we say it equals a forcing term here. And then, as I said before, to actually define the problem, we also need to define these boundary conditions. And so we say, we also have these boundary operators, and we also, there can be k of them. So for example, the velocity of the mass is 0 and the displacement starts at 1, for example. Those are two boundary conditions. And so we just apply those operators onto the solution, and they also equal some other boundary function. Okay, so that's framing the PDE. You can write pretty much any PDE in this term, like a wave equation, Helmholtz equation, Navier-Stokes, etc., etc. Yeah, and then the PINN, as I said, is just training a neural network, which is also a function of the input coordinates x, and has these 3 parameters, and it just approximates the solution to the PDE. And we have a loss function, which is, so now I'm going to call this the boundary loss. So this before was that supervised loss. So this is where we need examples of the solution on the boundary as our supervised loss here. And then the physics loss is minimizing the residual of the PDE as I described before. So yeah, if we just look at the expression of those terms, the boundary loss is applying those boundary operators to the neural network and minimizing the G here would be the labels of the solution, the examples of the solution. And then the physics loss is applying the residual of the PDE. Okay. So yeah, it'll be really helpful to give you an example of this. So I'm going to switch. Because I want to show you that we can apply this to any differential equation. So we're going to consider a different differential equation. This is the Burger's equation. And so the Burger's equation is really important for modeling fluid flow. And in particular, this is the viscous Burger's equation. So the fluid has some viscosity to it. And V here is the viscosity parameter, how viscous is the fluid. And U here just represents the speed of the fluid itself as a function of space and time. And so we can choose any kind of initial boundary conditions we'd like, but one of the most popular ones for like testing pins is this one where you start the fluid with a sinusoidal speed, and the fluid is inside a pipe, and so we say x is -1 and 1. The speed has to be 0 to constrain the fluid. Yeah, and so as before, we have the neural network is just representing the solution. This time I'm going to explicitly separate x and t to make it really clear. And then the boundary loss here, so both of our boundary conditions here are just constraints on U itself. So you can also have like constraints of the derivative of U, etc., etc. But for this, it's quite simple. And so the first one is, yeah, U of x at time equals 0 is sine of pi x. So how do we enforce this? We basically just sample lots of x's at time equals 0. So along that plane of x. And then we just enforce that the neural network plus sine of x tends to 0. So this is gonna enforce this first boundary condition. Then you can see the next ones do the same thing. So this time x is -1 at t at all times, and x is +1 at all times should equal 0. And so we're just gonna minimize that value. And then the final thing is the physics loss, and we're just changing the PDE here so that this is just the same as the Burger's equation. And we're going to sample these co-location points x and t every point in space and time. So this is not just on the boundary; it's everywhere. Okay, so how does that actually look? If let me give you a picture of this. And so this is a plot from the one of the most influential PINN papers. This is Rice's paper, which kind of introduced or reintroduced PINNs using kind of modern deep learning frameworks. And it's a very heavily cited paper. And this is one of the main plots from their paper. And so they're doing exactly what I just described, solving that problem of the Burger's equation. And this is exactly the same loss function that I just showed you in the previous slide. And so this is the solution to the equation. So U here is the speed of the fluid, and so what you see is we start. This is the speed of the fluid in the pipe, and we started with a sinusoidal speed distribution as a function of x. And what you see is very quickly a shock starts to form in the pipe, and this is why the Burger's equation is very interesting to investigate. But if you think about traditional finite difference methods, finite element methods, actually is really quite difficult to model this shock because it's a discontinuity. So this is a very interesting kind of problem to study in terms of simulation. So yeah, remember the boundary loss, we have these examples of the solution. So this is sine x sampled along this boundary here. So this is just t equals 0. And then these boundary conditions are certain that it's 0 -1 and 1 is just points sampled along the boundaries here. And then our co-location points, we just randomly sampled them across the entire domain. Does that make sense? Yeah? Okay, cool. All right, so here are some like specific parameters that they use. So this is the viscosity. They actually use 10,000 of these green points in the co-location points in the domain. So quite a lot. They use like random sampling essentially. And then just 100 points along the boundaries. And then you can see the type of network they used was 9 layers, 20 hidden units. So if you work it out, that's about 3,000 parameters. So not in terms of traditional machine learning, it's not a very big network at all, but it is enough to learn the solution here. And it's using a tanh activation function. Can anyone remember why tanh is important and not readers? Say again? Yeah, exactly. Yeah, exactly. So tanh is differentiable. Like you can get as many derivatives as you want from it. If you get the derivative of ReLU, it eventually becomes 0 because it's piecewise linear. So that's a really important thing. I always make that mistake when I'm coding pins. Yeah, and you see the neural network solution is basically bang on the exact solution in this case. And what's impressive is it gets the shock as well, to a good amount of accuracy. Okay, cool. So hopefully you understand how PINNs work for solving PDEs, and also in a general sense. So they're a general framework for solving these differential equations. So now what I want to do is like delve more into the actual training of PINNs and like the real nuts and bolts of actually coding them. And I think it's really important to understand some of these key training aspects. So let's think about how we're going to train the PINN. And we're just going to train it as if it was like a standard neural network, right? So we're just going to train it using gradient descent. And so how do we do it? So first we need to sample our boundary and our physics training loss points. So these are these orange and green values here. Then we're going to compute the outputs of the network. This is all very standard part of the training loop of neural networks. So then it becomes a bit trickier when the key difference here is we have these derivatives of the network with respect to its inputs. So this is very different to normal training of neural networks. The only derivatives we normally need when we train networks is the derivative of the loss function with respect to the weights of the network. So you see how this is a bit different. We've got something different going on here. So, but let's just imagine we have those, and then we compute the loss. But then once we've got the loss, we also need to compute the derivatives of the loss function with respect to the network parameters to use gradient descent. So somehow we've got to compute these derivatives, compute another set of derivatives by differentiating through that, through these derivatives in the physics loss. Okay, so we need to understand how we actually do this. Okay, so let's think about the first derivative that we need, the derivative of the network with respect to its inputs here. So how do we compute this? Okay, so let's make a couple of assumptions to think about it first. So we've got the vast majority of PINNs use fully connected networks, MLPs. So let's just assume we have like a 3-layer MLP. And what we want now is the derivative of the output with respect to the input here, T. And so it's actually very, very similar to how we use backpropagation to train standard neural networks. And we showed in the second deep learning lecture, the first deep learning lecture, that we can just use the multivariate chain rule to compute derivatives, and it's no different here. So the neural network here is composed of a series of functions, and we just say the neural network with respect to T is just this chain rule applied to each of those composed functions. And remember, each of these is actually, because we're multivariate functions here, these are Jacobians. These are actually matrix multiplies, as we discussed in that deep learning lecture. So actually for the MLP, this is analytically, it looks like this. It's just the weights times by these diagonal matrices. And the final value here is the first value of the weight, and that will give you the derivative of the network with respect to T. Okay, cool. So we know how to evaluate that derivative, so that's great. And the cool thing is we can just use autograd, because as I explained, autograd is a way of computing gradients of arbitrary programs, right? So it doesn't have to be a program where we want the gradient of the weights. It could just be a program where we want the gradient of the network inputs instead. And autograd would work in exactly the same way, where, remember I said autograd creates a graph, a computational graph where you have your inputs here, T, and these different parameters that you apply to it. And you can just put that as a graph, and autograd will then compute all of our vector Jacobian products if we're doing reverse mode differentiation. And it will communicate those backwards as a message passing through the graph, effectively evaluating the chain rule. And so the key realization here is, well, this is our expression for the derivative of the network with respect to T. This is just another bunch of computations on the weights and the outputs of the network and passing them through functions. So we can just think of this thing here is just another graph that is just applied on top of our existing computational graph. This is the forward pass, this is the derivative pass. So we just extend our graph with all these extra computations that are computing the derivatives. Can you see how that would work? Yeah, these are just basic operations, and we're just going to extend our graph with these extra operations. It doesn't actually matter that they're derivative operations. You can just think of them as more operations in the graph. And so the graph would look like this if we're doing forward mode differentiation. So forward mode, remember, is where we evaluate this derivative from the right to the left. So we start with the weight 1, then we times it by this diagonal matrix, etc., etc. And obviously, if we do weight 1 times this diagonal, we get dh by dt, and this is applying the chain rule in forward mode. Okay. So this is actually really great. This means we can just recursively do this. We can compute the derivative, and then we can just extend the graph, and then we can compute any derivative on top of that new graph, extend the graph again, compute a derivative, etc., etc., etc. And you can combine whatever different gradients you want and add them to the graph however you want. And this is really the power of autodiff, is it's like arbitrary programs. You can see how this would let us get not only the first order gradient, but also the second order derivative that we need, for example, in that damped harmonic oscillator loss. Okay, so how does the training loop look? It's to compute these gradients, we just apply autodiff and extend the graph. And then when we come to get the loss function, we just do autodiff again on that extended graph, but the final gradient is now with respect to the weights instead of the inputs of the network. And what's really great is these modern deep learning frameworks, I'm showing PyTorch here, just allows us to do this in just a single change of the line of code. So how would this look in PyTorch? So first you would, T here is my inputs to the network, theta is the free parameters of the network. So for that damped harmonic oscillator, for example, I needed the first order derivative with respect to T and the second order derivative with respect to T. And so I just apply it, grad here computes the gradient of U with respect to T. And I add this extra parameter, which is called grade graph. And that instructs autograd to extend the graph and remember it so that it can differentiate through it again if we want to. And so we do need to do that because we want to compute the second order derivative. This time it's du by dt with respect to t. And then finally, when we collect all these guys together, we compute our physics loss with them. And then we do the final differentiation is the gradient of the loss with respect to theta. And so that's how we can use kind of autograd and all of its power to actually train pins and evaluate its gradients. So I mean, it's great from a programmer's point of view. We only have to change one line of code, but actually it's really sophisticated what's going on in terms of autograd to actually be able to train this pin. And I think this is one of the reasons why pins had this resurgence in like 5 years ago when that Ricey paper came out. It's because we realized autograd is powerful enough to do this stuff for us, and we don't have to by hand compute all these analytical gradients, which is really, really laborious to do. Okay, so I'm hopefully going to show you how to do this in PyTorch, and I know some of you hopefully had a go at this in the tutorial last week as well. So hopefully this will be a nice refresher for you. I'm gonna switch my sharing screen for you guys online. So let me just go to Google Chrome. Okay. Okay, so what we're going to do is we're going to train the pin to solve this damped harmonic oscillator that I showed you at the start. And so I'm just going to zoom in a little bit. So yeah, this is the oscillator. And the problem setup is exactly the same as I was showing in the slides. So again, we have the mass here, the coefficient of friction and the spring constant. And you can do some really, this solution, this differential equation has an exact solution in this case, and it's very well studied. And there's some really cool physics that happens, but there's one particular state that we're interested in, which is the underdamped state. And this is where the solution just decays slowly over time with an exponential decay and an oscillatory kind of solution within it. And so the exact solution in this case is given by this expression. So if you're interested in the math behind it, definitely have a look at this link. It's really, really interesting. And we're going to first focus on this first task. We're going to simulate the system using the PINN. Okay, so we just need a couple of like initial setups of the code. So first is just a simple function that defines what that exact solution is, just so we can see how well the PINN's doing. And then the second one is just defining a standard fully connected neural network in PyTorch. And so I'm not going to explain how this works exactly. Hopefully you understand this from the previous tutorials. But one of the important things is we have this activation, which is a tanh activation function here. Okay. So how are we going to train the PINN? So again, the neural network is just a functional approximation to the solution. And we're going to choose a couple of parameters, like fix them. So for example, this delta and omega 0, which is just, they just depend on the coefficient of friction and the spring constant. And then the loss function, we're going to have our boundary loss, and we're going to assert two things. We're going to say the neural network at time equals 0 is going to be a displacement of 1. So it starts up here. And the other one is that we're going to make sure the velocity is 0, so it starts stationary. And so we're going to have, the neural network of 0 is 1, and then the derivative of the network with respect to t of 0 is also is 0. And then we're going to have our extra physics loss term on top. And yeah, as I said, we're going to apply torch.autograd to get these gradients. So I'm just going to, so what I've got here is like a bare kind of training loop, and I'm just going to fill in the most important bits to understand. So first of all, we just need to create the neural network in PyTorch. And so this is just going to be kind of 3 layers and 32 hidden units. And so the first thing we need to do is define 2 sets of points. First is the boundary point, where we're going to evaluate the boundary loss. And the second is the co-location points. So these are the points across the domain that we're going to evaluate the physics loss. So how do we do that in PyTorch? So we can do t boundary equals torch.tensor. And so we only need 1 point here. This is t equals 0. Because this is just a one-dimensional problem. So t equals 0. And so one really important thing we need to do is we need to do this thing called requires grad. We're going to say equals true. So does anyone know why we need to do that flag in PyTorch? Say again. Yeah, so for computational efficiency, PyTorch doesn't by default track the computational graph that you're doing in PyTorch. So you have to explicitly say, I want gradients with respect to this tensor, which we do. So we're going to do that. And then we're going to just make sure that it's a nice shape for the input of the network. So remember, the network in PyTorch has a batch dimension here and then a channel dimension here. Okay, so then we can do the same thing for the physics loss. So now for this case, we need to sample points across the whole domain, right? So that we can make sure the residual is 0 everywhere. And so what I'm going to do, I'm going to use a line space between 0 and 1, and I'm just going to choose 30 points. So for now, it's just going to be regularly sampled, but they can also be randomly sampled. It kind of depends. This is like a hyperparameter choice that you need to choose. Again, we're going to requires grad. And then we're going to make sure that the shape is nice as well. Okay, cool. So that should be fine for this part. So then we're just going to set up our optimizer. This is standard PyTorch stuff, make sure the gradients are 0 to start with. And then we need to compute our boundary loss and then our physics loss. So these are the next 2 steps. Okay, so what's the boundary loss? We have 2 terms. So the first one is very simple. We just want to make sure the neural network of 0 is close to 1. So we need to do u is the PINN as a function of the boundary point, like this. And then we say our first loss is just u minus 1, like this. So we're just saying the neural network is 1. And then we're just going to square this. And the other thing we want to do is just squeeze this into a single scalar value. So this is just 1 point, so we're just going to squeeze it. Okay, and then the next loss we want is the derivative of the networks. So the velocity of the network should be 0. So this is where we need to use autograd. So let's do that instead. So u is torch.autograd.grad, and then we want u with respect to my boundary point, like this. There's a couple of other things we need to do. We need to, so remember, autograd is not actually computing the Jacobian, it's computing the vector Jacobian product when we're using reverse mode. And this is like for efficiency reasons. So if u here is not a scalar, then we also need to define what the vector is that we're applying to that Jacobian vector product or vector Jacobian product. In this case, it is actually a scalar, but because the shape's a bit weird, I'm just going to give it a value of 1. So I'm going to do torch.ones like do. And then the final thing we need to do is this create graph thing, because we're going to be using this in our actual loss function, like this. And I know that it produces a tuples output, so I just need to grab the first output of the tuple. So yeah, hopefully this is going to compute this, and then we need to compute the second loss term, which is u minus 0 squared, like this. And then we're going to also need to squeeze this like we did for the first one. Okay, so hopefully that works. So that's the boundary loss. We've done the first 2 terms. Now we need to do basically the same thing for the physics loss, and it's very similar stuff. We're going to be using autograd to get the gradients. So again, we need to get the forward pass of the network. So this time we're going to apply it to the boundary, to the physics points. These are these physics points that we created up here. And then I'm just going to copy and paste this and change it a little bit. So we need u with respect to t physics now. And here we need the second order derivative. And so we just do exactly the same thing. But now instead, remember we're creating a graph here. And so this is just part of the computational graph, and we can create a derivative of this this tensor with respect to whatever we want, actually. So we're going to do du by dt physics to get our second order. Okay, and then the final thing is to get the loss, the physics loss. So loss 3 equals, and this is where we assert our differential equation. So we just do. I'm just assuming that m is 1 for this problem. So we're going to get rid of m. We're just going to do du plus what is it? It's mu times by. Give me a sec. U squared by mu plus k times by mu. So that's our PDE, and we want to make sure that this is as close to 0 as possible. So we're just going to square it, and then we're going to take the mean over those points, those 30 points that we started with. Okay, so I'm going to try and run it to see if there's any bugs. If there is, I'll try and fix them. So torch is not defined, yeah, so we haven't run anything. So let's run stuff. Okay, so we just need to import, and then we need to exact solution. Let's try. Cool, so it's working. So what I'm plotting here is the co-location points here, the green points. The red point is just the boundary point that I'm training with, and then the green is the neural network solution as a function of the training step, and then we've got the exact solution to compare to. And so, yeah, you can see it's just training. It's taking a little while, but not too long, maybe 30 seconds or so, and is eventually getting to the solution. So yeah, hopefully that's showing you that it's very easy to code like a basic PINN in PyTorch, and it can run fairly quickly as well. Okay, so let's switch back to the talk. And we're just, before we take a break, we're just going to have, there's two extra slides that I want to talk about with the training of PINNs. I'll just change this. So the first So the first is that is actually the computational cost of computing these gradients with respect to the inputs. So I try to convince you that AutoDiff, when we're training normal neural networks and getting the gradients with respect to its parameters, is a very efficient algorithm. It's probably optimally efficient. Remember, we use a bunch of tricks, and especially when we're computing our vector Jacobian products, to make sure that the back propagation is just a bunch of vector matrix multiplies, which is very, very quick. So, and you can actually show that if you have some function here, which is a vector function, and you have its Jacobian here, and some vector that you're going to apply to that Jacobian, you can actually show that when you're using AutoGrad, the time to compute the function in the Jacobian vector product is actually less than equal to a constant value times by the time it actually takes to compute the function. So that's great. That's basically linear time to compute your Jacobian vector product. But the key thing here is actually this constant, and this constant is usually around 2.5. And so if we're going to compute JV, so Jacobians in multiple times, we're going to be basically timesing by 2 each time. So that's actually exponential. If we want to compute like dn by dt up to the nth order, that's going to grow exponentially with n. So PINNs, this is a limitation of PINNs for sure, is a lot of the time is actually spent computing these gradients, especially when you have PDEs that have higher order derivatives, like second order, third order derivatives. So most of the time is spent computing those and not in the forward pass. And so that's something to consider when you're thinking about using PINNs for your PDE. If you actually want to understand the detailed derivation of this, you should definitely check out this book. It's very, very clear derivation. And then there are also a lot of other things that you have to think about, and hopefully you might have experimented with these in this tutorial. So one thing I haven't said anything about so far is this lambda parameter. And so what do you think the purpose of this lambda value is? Anyone know? Go on. Yes.
Basically, to constrain the polarization and
yeah. Yeah, exactly. So we have two loss terms here, and we need to make sure that they're balanced. So you can imagine if one is too big compared to the other, what might happen? So for example, if the physics loss is too big and the supervised loss is basically 0, then the network's just going to learn a random particular solution of the equation, and it won't match what this is. The other way around, if the supervised loss is really large, then the collocation points won't matter, and it won't learn an oscillatory process. So yeah, lambda is very important. And it's also important to note that if you're thinking about the physics of this and the actual units of these quantities, like the unit of this is displacement, it's like m. But the units of this is like acceleration, because we've got second order derivatives here. So again, the units are not going to match. So that's another reason why lambda has to be changed. By the way, I'm going to cover all of these different considerations next lecture in way more detail, and the impact that has on the PINN. But briefly, another one is you need to make sure you have enough co-location points. Otherwise, again, you're not going to fit the solution over the entire domain. And same with the boundary points to ensure the solution is unique. And then it's very much up to you how you choose those points. So they could be randomly or regularly distributed. And then the final caveat is, like, from a machine learning angle, like PINNs are just neural networks. And again, they suffer from exactly the same error problems that I was talking about in the second deep learning lecture. So, estimation error, approximation error, optimization error, they all still exist. And so you have to think about that too. Okay, so let's take a short break, and then we'll get back to the rest of the lecture.
So here you said that you need enough collocation points to do the job. So both in time and space, right? So for example, when we're like solving the flow equation, like time equations, some of the problems we need to march in time, and to march in time, and then each iteration you need to solve a like space problem. So is there like a multi-sibling approach to like?
Yeah, this is definitely an ongoing area of research. It's to figure out how to, especially time-dependent different equations, how to solve forward in time. You can just brute force it and like get about millions of co-location points, predict it to one of the global population, and just hope that the boundary conditions get propagated forward. But there are other I'm going to talk a lot about this next lecture. There are like tricks that you can use. For example, you can change the density of the co-location points and let the density like propagate outwards in time, so that you start by preferring to learn the solution in time equals 0 and like learn it outwards from. Does that make sense? So you start with basically you start with any points that are just like at time equals 0. You don't have any other co-location points. And then you extend the horizon at that time a little bit, and you say, okay, now I'm going to start co-location points from like 0 to down.
Yeah, but we still need to solve it forward.
Yeah, so as training progresses, you slowly expand the like maximum time of the co-location points, and then the network like starts to learn outwards a bit more.
It's like they go to each other.
Yeah, these are not principles. These are like tricks and like things that we're still experimenting. I'll talk about that.
So for now, I'm thinking like more powerful and
what I'm going to get onto is I personally think the forward models or forward problems, they're not competitive for a bunch of reasons I'll get onto that. But they are very useful for like, other applications like inverse problems and equation discovery. That's what so I'll get to that. Yeah, all good questions.
In your
negative. Oh, I see. Yeah. Yeah. I think what you'll find. Yeah, I think what you'll find is the network's not going to work.
Yes.
So there's no free lunch. So people get excited because they're like, oh, we're going to constrain by physics and it's going to generalize. It doesn't. Yeah. Oh, for exactly the pipe.
Yeah,
I think it would give you a really weird solution that you just get across. But at the pipe location, it would be exactly what you want to do. So 0 and a derivative. Yeah.
And the thing we talked about the if we go like points which should be big outside of either above 30 or below 0, or if it's like it's below 0, the big difference is exactly always
But I would only trust the solution inside the domain that you've trained on. Anywhere else,
not even most of it. It would say that if you were like a point like 30.
Yeah, so this all depends on the prior of the neural network. So what are the functions of the neural network likes to represent when it's not been trained? And that would basically be you would be relying on that prior when you go a step outside of the training process, which is basically like its initial value essentially. So it's whatever kind of the architecture decides. Yeah, exactly. So if you choose an architecture which has some prior, like an oscillator, then it might generalize way better. And I've got some examples later. Good question.
I didn't understand the right.
Yeah.
But here we have just on top of the normal variables for the weights, we have this additional limit for the time this differential equation.
Yeah. So the whole point here is you can just think of these as mathematical operations. Like, so to get this derivative in, you can do a bunch of mathematical operations like this, multipliers and sort of bunch of multipliers, which are just
think about a computational graph. So it's inputs to that graph, just the inputs in my existing graph. So we get that these have derivatives, but it's like a bunch of operation. And then the whole thing is just a new graph. If we have an output and we want it to differentiate through that, we get other leaves of the graph.
There's been a derivative.
Yeah, mathematically there are derivatives, but computationally they're just operations.
Yeah.
Does that make sense?
Yeah, I think so.
So that's why you can just extend.
Okay,
Extend. As you compute the derivative, you can just build the graph as you go. Then different again.
I'm not entirely sure, but now it makes sense.
Yeah.
And just a question about this. I haven't got to hear this progress. Can you explain this question? I mean, I don't get how this is the position.
So this is the same in all network. All values are X. So this is the just saying that cost sign of this. So if you minimize that thing, that's going to say we want the network to be close to negative sign.
What do you think the sign here?
So this is just our choice of the initial connect. Because it just produces this nice shot. Again, I like to study this computation problem. It's completely arbitrary, but you can choose whatever you want. It's just the initial profile of the fluid.
But how can you mention that? I mean, there's a fluid coming in this tube.
Yeah, so it's just you can think of it as like a cross section of a pipe, and we're just measuring the speed of that cross section. There's a function of time. Yeah. So that's what's showing. This is not really the fluid anything that way, and it's just at like a single point that's in the product. Starting with Simon Fluid distribution, and it's quickly become so the fluids, because it's -1 and 1, some of the fluids moving this way, so that's really power.
Okay.
With a nice smooth change. But then at later times, you then get a very quick shock, which basically says half of the fluids moving out, half of the
This is the shock.
and there's a discontinuity.
Ah, nice.
So that's what it's.
Okay. Maybe I should study the Burgers equation.
That's okay. It's
That's just what we pick up in the doctor's boundary conditions. Okay.
yeah. So
But
that's
basically, it's the velocity.
yes. Speed of.
Thank you.
Yeah, no problem.
Thanks.
Okay, we're going to get started again, everyone. So I gave you a recap of what pins are, and then I told you a bit more about how we actually compute gradients of pins, and I live coded a pin for you as well. So now we're going to talk more about more applications of what can we actually use pins for, and I've already shown you that they can be used for simulation, and they're a very general purpose technique for solving PDEs. But what's really great is they can also be applied to these whole other scientific tasks that are really important. So for example, they can be applied to inverse problems, and they can be applied to equation discovery. Okay. So I want you to remember back to the very first lecture where we were kind of motivating the entire course. And in that, I tried to tell you these 3 different scientific tasks that are just generally really important across many different domains of science. And so I gave you this example of like seismic waves like propagating through the Earth, like with some velocity model of the Earth. But I encouraged you to like abstract the idea into like any scientific problem. And typically what we do is we have kind of 3 big tasks that we want to solve. And we say, well, given some we have some system, and given some like inputs or initial conditions of the system, which we just call A, we have some outputs of the system, like some observables, which we're calling B. And we have some physical way of solving that system, like a finite difference solver, for example, which tells us the relationship between the inputs and the outputs. And so depending on what we're interested in gives us a different task. So like, for example, forward simulation is just, given the inputs, what are the outputs of the system? But we also have these two other tasks which are really important, which the first is an inverse problem, which is like, given the observations of the system, can we actually invert for its underlying parameters? And then the equation discovery is actually, can we learn something about the system itself? And so these are like big, broad areas of scientific problems and really interesting to investigate. And yeah, so for example, with this wave equation example, the simulation is like, given the velocity model and the location of like a source of the earthquake, what's the resulting displacement of the Earth, or the wave field, we call it. Then the inverse problem is like, given measurements of that wave field, can we actually understand what the structure of the Earth is, or the velocity model, and where the source was? And then the equation discovery is like, given all of this data and information, like, can we actually figure out the underlying physics, which is the wave equation itself? And so it turns out PINNs can actually be used for all of these different tasks. And at the moment, we've only covered this first task, which is this forward simulation. So yeah, here's just one more example of using PINNs for forward simulation. This is some work that we did in our lab. Again, trying to solve the wave equation. So the setup is very, very similar. Again, we have a neural network here, and in this case, it's a two-dimensional problem plus time, so 3D in total. So we have this wave that's propagating outwards through this velocity model, starting in the middle of it here. And you can see as the wave kind of propagates outwards, it starts reflecting when it meets a contrast in the velocity, and it also starts to get squashed and expanded depending on the velocity it's currently in. So you get quite a lot of complex physics that happens in this system. So that, yeah, the network is just giving my two input coordinates, x and y, or x1, x2, and then the time here. And then the output is the displacement. So this is the wave field itself of the wave. So yeah, again, we have a boundary term, and we have the physics term. You can see the physics term here is just putting in our wave equation, which is the underlying equation here. And as part of that equation, we have the velocity model, which is c is a function of x. So this is this velocity model here. We're just gonna say that's a function that we can evaluate at any point in space. And then the boundary data. Well, in this case, what we did is we actually ran finite difference simulation for like 2 time steps or 3 time steps, just to get the examples of the wave field at the start. There are different ways you can do this, but this is how we chose for this paper. So only the first 0.2 seconds. So basically this red box. So the network didn't see any of the data beyond it. Yeah. So I mean, if you train the PINN, you get a really great result. It does learn to propagate the wave field outwards. And what's really cool is it starts to learn simulate these reflections as well, and the compression of the wave field. Something that it didn't see, and it's like in that finite difference data that we trained it with. And this is all because of that physics loss term. So that's really great. And the other thing we compared it to was just a network that was trained without this physics loss. So we just trained it on this like first couple of time steps of the FD simulation. And so what you can see is the network like learns the boundary, the initial condition very well, but then and what's interesting is it also learns this like general idea of the wave field like propagating outwards, but doesn't get any of the extra stuff that happens once it hits like an interface and starts reflecting, for example. So you can really see the power of the physics loss here. Really regularizes our solution. So this is a couple of things. The most interesting thing here is the training time. So this simulation. So this is a 3D simulation. So we had to generate points in a 3D space, and so this is another limitation to PINNs. Is as you go to higher dimensional problems, you have to sample co-location points in higher dimensions, and so that's great. The number of points like can grow exponentially that you need to like properly sample that domain. And so so instead of sampling thousands of points or millions of points, we did a mini batch. So we randomly sampled just 500 points in the domain, and then changed the number of points every training iteration, so to make sure that we eventually covered the whole domain. But this network we had to use a bigger one because it's a 3D problem, and you can see the solution is actually quite complicated. So this is 10 layers, 1,000 hidden units per layer. So if you just if you just add all those things up, it eventually means you have to train for longer. And this is actually a fairly big issue, and I'm going to talk about this in the next lecture about you know, if I ran finite difference simulation for this, it would take of the order of like a minute or something. And so, you know, this is a big limitation for this particular problem. Okay, so that's enough about simulation. So what about inverse problems and using pins for inverse problems? Okay, so let's think about that problem again. So we have the wave equation here. And so now the problem we want to do now is we don't want to simulate the wave field. We actually want to, given values of this wave field, we want to understand what the velocity model is. So in terms of the wave equation here, given observations of u, can we figure out what c of x is? So what is this function, and what is this velocity model? And so as I was explaining in the first lecture, like inverse problems are really, really hard to solve. And the way that you typically solve them is frame them as like a search problem. And so you say, okay, let's just abstract to that more general setting where you've got some physical system, inputs and outputs. You just say, I want to minimize this thing, the difference between the observations of the system and what my forward model predicts given the parameters. And I'm going to change the input parameters to try and best match my observations. And so that's how we would traditionally set up our inverse problem. And yeah, this is a slide taken from the first lecture, and I was saying from that lecture, the inverse problems are really challenging to solve. You know, they're typically very ill-posed. So this means that there's not enough observational data here, or for example, wave field observations here, to uniquely tell us what the underlying parameters are, so what the velocity model is. And the observational data that we have is typically very noisy and very sparse as well. So that all makes it harder to solve. And then the final thing is that running this simulation, this forward model, typically we need to run it like thousands of times to solve this optimization problem. And so that can be very expensive if this forward model is like a finite element solver, for example. So these are the big challenges of inverse problems. And I showed you this other example of computational tomography imaging as well. Suffers from the same sort of issues. Okay, so how are we going to use a PINN for inversion? So let's just start off again with our loss function for forward simulation. So this is just, again, we have our boundary loss, our physics loss. This is exactly the same as I showed you in the last part of the lecture. And for example, like if we're doing the wave equation, D here is the wave equation operator. Okay, so to do inverse problems, it's actually very, very simple. We just make a few changes to that loss function. So what we do, the most important change is, well, so we realize that this operator here, the differentiable operator, which is just defining our PDE, it has some of these terms here that we actually want to know. We want to know what the velocity of the Earth is here, for example. And so what we do is we say, okay, we don't know these. We're actually going to learn these instead. So we're going to treat C as a learnable parameter in our loss function. So we say, in general, like our differentiable operator here just depends on some underlying parameters that we don't know. And we're just going to say they're just learnable parameters, just like the thetas of the neural network are. So we're just going to say, as well as optimizing theta, we're going to optimize phi, or our parameters of our underlying PDE. And how can we do this? Like, is this even possible? Well, yeah, sure. It's very possible, because as I talked to you before, autograd is this thing that allows us to compute arbitrary derivatives. So we use autograd to get derivatives of the loss function with respect to theta, of the network with respect to x. We can also get derivatives of this loss function with respect to the parameters of the differential operator. It makes no difference if you're just thinking about the autograd, how autograd works. So yeah, we can definitely try to learn these. So that's the big change that we make to the physics loss. And then the final thing we do is, well, we probably don't know what the boundary conditions are now. Just say that we're given some, like, for example, in the wave equation, we're just given some random observations here. They could be at any point in space, not necessarily at the boundaries of the problem. So we'll get rid of the boundary loss, but instead we'll add just a very simple data loss. And that's just saying, wherever we have these observational points of the outputs of the system, we're just going to make sure that the neural network has a supervised loss that makes sure that it equals those points where we know them. So this is our data loss here. So yeah, these are the two changes. We add or we treat the parameters of the differential equation as learnable parameters, and then we add a data loss which makes sure that the observational data is minimized in a supervised way. So that's it. And the cool thing is we simultaneously learn theta and phi when we're training the PINN. And so this is really cool because when you train the PINN, it not only learns the solution, but it learns those underlying parameters. And so what it's doing is this kind of joint forward simulation and inversion at the same time, which is really cool. It's a very different way to think about solving inverse problems. The way that we did it before is we would just F here is just a finite difference simulator. We don't learn that. That's just a function that we call. And so it's kind of exact every time you call it. But when you're training the PINN, you're kind of simultaneously learning the simulation and learning the inverse problem at the same time. So it's a very interesting kind of new way to do it. Okay, so let's make this more concrete and let's go back to that wave equation problem that I showed. And so yeah, what's the inverse problem that I said? We have these observations of the wave field, and we want to figure out what's the underlying velocity model that this wave is propagating through. And so this problem here that I'm showing, what we actually have is like a plate. So it's just like a 2D metal plate, and that plate has like a crack in it somewhere. And in terms of the wave, the way that that crack affects the waves is it's like a velocity perturbation. So it like starts reflecting some of the waves. And so you can actually see like there's something weird going on here. It's probably where the crack is. And so what we're doing is we're just vibrating this plate from like a single source. And then we're measuring the displacement of that plate at every point of that plate. So this is the plate itself, and this is the displacement of the plate. And we know that this is just a wave equation. This is exactly what's happening. So we have exactly the same physics losses I used in that previous PINN that was just solving the wave equation. But the only difference is that we're treating the velocity model here as like a learnable parameter. And what's really cool is, well, actually, this is not a scalar parameter. This velocity parameter is actually a function of space. Like the velocity here is going to vary every point in space potentially. And so how do we learn that instead of just a single value? Well, the really cool trick is that we can also say that the velocity is just another neural network that's going to approximate the true velocity function itself. And so you actually set this problem up with two neural networks. You say, the first one here is just a function of my inputs and outputs. This is just the PINN that's going to learn the simulation. And then this is the extra neural network, which is going to, again, has the same, actually, I've got this wrong. This shouldn't have a t here. This should just be as a function of x and x1 and x2. And this just learns the velocity field as a function of space. And it has these other parameters, phi, which we're going to train. And then we just chuck in our observational data. These are just you can see these are real measurements of the wave field. So these are like speckly measurements. So we're just going to add that into our data loss. And then we'll just train it like just as we would train any other neural network. And so yeah, this is the result that this paper got. This query. What they're doing is they're querying this learn velocity network to see how the velocity varies across the plate, and you can see that the PINNs learn to invert for this crack, and it shows up as like a perturbation in the velocity.
So
yeah.
We're like framing this learning problem as like minimizing LP, but at the same time we have this we have this data parameter in the minimization problem.
Yeah.
So like how do we actually optimize this? Yeah. So we're optimizing two things. We're optimizing the neural network, which represents the solution of the differential equation, and then we're optimizing also the velocity inside that differential equation.
And the cool thing is we're doing both of those at the same time. So you can think of the neural network is just trying to fit the wave field that we have, the observations that we have. And we have a lot of observations, like the wave field at every point in space, basically. And so as the network does that, when you're training the PINN, that means whatever residual differential equation it's using, that has to be the true differential equation to fit that data. And the only way that that's going to be true is if that differential equation has the correct velocity model inside of it, that we're also learning at the same time. Does that make sense? So the caveat, and this is the same with all inverse problems, is you have to have enough observational data to make sure that this problem is uniquely posed, so that there is only one velocity model that could possibly explain all this observational data. But the PINN still has the same limitations as I was saying before. Like we need to have enough data, and it needs to be relatively noise-free to be able to do this properly. Does that help? Yeah.
And sorry, and
yeah,
it's about like we separate two this two neural networks.
Yeah.
As like architecture.
Yeah.
Or...
So you're free to do what you want. So you can, in this paper, they just use two neural networks, very independent. But you can play around. Like you can have an extra output node of this network and just call that C, and whatever you like. So yeah. Did you have a question up there? You're covered. Yeah. Okay, perfect. Yeah. Any other questions? This is fairly hard to understand, I guess. So. Yeah.
So imagine if we have successfully fueled the lower loss L0.
Yeah.
So it might be a possibility that in fact the output of this neural network fits the data, but
yeah.
The derivative does not fit the PDE regularization.
Yeah.
In this time, if you when you are training the upper loss, if you fix the data, now you have perfect.
Yeah.
And probably there will be a possibility that because the neural network is wrong in the sense of PDE loss, then you will get also a wrong C.
Exactly.
So that means so you have two wrong things, but when you combine it, then it's correct.
Yeah, so exactly. So you can do this. You can choose how you want to optimize this. So one way is exactly as you described. You could say, I'm just going to fix the differential equation and just, I'm not even going to use the physics loss. I'm just going to train the network first as like a pre-training to fit the data. And that's a great step, actually. That's probably a good idea. And then you can fix the neural network weights and then train the phi's instead, the next neural network. And maybe that would work better than if you did it jointly. That's actually a good research question because it's interesting to know how best to do that. But going back to your point where the gradients could be wrong, for sure they can be wrong, especially if you don't have enough data. This all depends, again, on is the problem well posed? So do you have enough data to uniquely define what the underlying parameters are?
Sorry, following this question, you mentioned that we need enough boundary points to make sure that underlying PD has a unique solution.
Yeah.
Do we have actually an estimate or
so we don't, in general, for inverse problems, you don't have, you don't assume you have that. You might have that. So for example, here we do, because we have the wave field at every point in space. But again, this just comes again down to the ill-posedness of the problem. Is it sufficient if you don't have boundary conditions, but you do have some other observations inside the domain somewhere? Is that still sufficient? And that really just depends on the PDE and the problem that you're thinking about. So, yeah. Okay. So I'm going to do this again in our previous PyTorch session. So we're going to go back to the 1D harmonic oscillator, and we're going to do that. We're going to solve the inverse problem instead of the forward problem. So again, I'm going to swap screens. Okay, so this is the PINN that we had before. We've successfully trained it. So now we're going to do the inverse problem, and so what we're going to do is we're going to have some. We're going to do the same loss function. Oh, no, sorry, we're not doing the same loss function, but we're going to have the same physics loss. But inside that physics loss, we're going to assume that we don't actually know what mu is. And this is the question that someone asked right at the start of the lecture. So yeah, we're going to assume mu is not known, and we're actually going to treat it as an additional learnable parameter in training the PIN. So we're not using an extra neural network here. We're just going to learn a scalar value. So it's going to be way easier. So yeah, we have the same thing, but inside our loss, mu is now a learnable thing. And now we don't have a boundary term. We're not going to assert boundary conditions, but we are going to say lots of points that we observe, the neural network has to match those points. So in particular, I'm going to create some noisy observational data. So these are like observations of the solution that we actually have. And I've added a bit of Gaussian noise to it as well, so that it's not perfectly sampled data. So yeah, the inverse problem is, like, given these observational points and given this differential equation, can we figure out what mu is? And we're going to train the neural network again to fit the points. But at the same time as the neural network's learning to fit those points, we're also going to be learning mu. And we're going to hope that this converges, because this is hopefully a fairly well-posed problem, because I've got lots of points along the curve. Does that make sense to everyone? Yeah? Okay, so I've already created some data. These are just my observational data here, U and T. So the first thing we need to do is we need to create a new parameter in PyTorch that is going to be learnable. Okay, so we're going to say mu. So we don't know what the value of mu is anymore. So I've blocked out the value of mu here. We don't know what it is. So we're just going to say, okay, it's going to be, well, actually, we just to help PyTorch, we're going to wrap it in this thing called a parameter. Let me just go back to here. So we do neural network.parameter, and then we create a tensor. So we need to pick, like, as you do with any inverse problem, what is your like initial estimate of this parameter? So I'm just going to say initially, we're just going to say it's 0, for example. But obviously that's not the true value, but it, so that's basically saying there's no friction in the system to start with. Cool. And then we also need to, again, we're going to be updating this with gradient descent. So we need to make sure that PyTorch tracks the computational graph, just the same as we had for those other tensors we were creating. So we're going to do requires grad equals true. Cool. So yeah, that's that setup. And so then we need to make sure that our optimizer in PyTorch is going to optimize mu as well as all the parameters in the network. So I'm just going to copy and paste the code from above. This is how we define the optimizer in PyTorch. Let me just paste it down here. So this is our optimizer. And before, to create this Atom optimizer, we said we want to optimize the parameters of the PIN. So we need to add mu as an extra parameter inside this optimizer. So the way that we do this is we just turn this thing into a list, and then we just add mu we extend the list with that extra parameter. So all I'm doing here is saying the Atom optimizer, as well as optimizing the network parameters, I want to jointly optimize mu. Okay. And then I've copied and pasted the physics loss from above. That's exactly the same. There's no change. We don't have a boundary loss anymore, but we do have this data loss, which is this extra loss term. So this is saying at the data points, it's a supervised loss to make sure the network matches them. So let's go ahead and compute that. We're going to say, again, we need to run the PIN at the observed locations. So these are just the coordinates of those locations. And then we're just going to do a mean squared error loss. So loss 2 equals torch.mean of u minus u obs squared, like that. So yeah, very simple. Network needs to match these observational points that we have here. Okay, I think that should be everything. So everything else stays the same. Like the way we create the loss function, we just optimize it with respect to the parameters of the network and mu. And then we're just going to save the value of mu as we run, so I can plot it. So yeah, let's see if this runs. Okay, cool. So that's running. So yeah, again, we're showing this as a function of training step. These are the noisy observations. This is the PIN solution. And this is the true value of mu up here. And then this is the value of mu as it's learning. So remember we started off with mu equals to 0. And this is exactly what we were saying, that what we're doing is we're jointly learning the simulation here. and we're learning the inverse problem, like the parameters of mu at the same time. And you can see, because this problem is well posed, this actually nicely converges. Like the loss function is nice enough that we can converge to the minimum of the loss function. And so, yeah, as the PINN trains, maybe we overshoot a little bit, but eventually we converge to the true value of what mu is, and we end up with a nice value of mu and a nice fit to our data. So this is really nice. This is extending PINNs to solve like these complicated problems where we actually have some data and we want to understand something about the PDE itself. All right, so let's go back to the PowerPoint. Okay, so yeah, this is really great. So now we can start adding data to our PINNs and like learn stuff about the PDE. And so I've just got another example here of a different inverse problem, just to show you, just as before when we had when we can use PINNs to solve any general PDE, we can also use PINNs to solve any kind of general inverse problem as well. So this is a different inverse problem. This is looking at cardiac activation mapping. So this is a really cool like area of research. What basically we want to track the activation maps of your heart as it beats. So when your heart beats, you can think of it as like a wave that's propagating outwards. And as the wave propagates, when that wavefront hits a part of the heart, that gets activated. And so what these activation maps are showing is like the time of the activation. So you can see the wave started at some point here, and then it propagated outwards, and the activation time is like the time it took to travel from this source location to wherever that point is. And so we want to understand, it's really useful to understand these activation maps to like study the heart. But what's also interesting is these waves are propagating through the heart, and the heart doesn't have a constant velocity. It actually has a varying velocity. So this is kind of like the wave equation again. The actual equation is slightly different. It's called the Eikenor equation. And this is because we're not actually interested in the displacement of that wave. We just want to know what the travel time is and the velocity. So we can kind of simplify the wave equation in a way. So t here is like the travel time as a function of location. And v here is just the velocity of every point of the heart. So you don't have to apply this equation to the heart. You can also just make it simpler and have like just a 2D medium, which has like this velocity model here, which is just like one value over here and one value over here. And you can do so. This is the velocity, and this is like the activation times. Yeah, and so we can train the PINN to solve this equation. Basically, the simulation here is to simulate the activation times given the velocity model. But the inverse problem is given like observations of these activations, can we figure out what the actual velocity model of the heart is, or of the medium that it's traveling through? And so, yeah, again, we have these observations of the activation times. We can just sample it at every point on the heart. And we know what the physics loss is. We can have another neural network which approximates this velocity model, just as we had in that previous inverse problem. And we can train the PINN to try and get to figure out what this velocity model is. And what you can do is you can compare it to like interpolating the results instead. So in this way, you can think of the PINN as doing like a nice interpolation of my activation points. And what you find is because we have this like physics loss, we can actually interpolate these points way better than if we just do like a standard neural network or like a linear interpolation, for example. So there are many examples of like using PINNs for like inverse problems in the literature, and it's very, very interesting area. Okay. Okay, so let's go one step further, and this is the last part of the lecture is to say, okay, instead of just like learning about like single parameters in my differential equation, can I actually discover the differential equation itself? And this is going into the area of like learning physics, or like, learning underlying like laws of systems. And it's like I said in the first lecture, that's kind of traditionally depended on like our remarkable human intuition. And there's a question is like, as AI machine learning gets more and more advanced, can it start to learn these laws itself? And so you can do you can use pins to do this in like a very specific way, which I'm going to describe. So yeah, this is how we set the pin up for the inverse problem. We said, okay, well, our differential operator here has some free parameters, and we're going to also optimize them as we learn the solution, where we have some observations of our system. So the question that we want to ask instead is, instead of just learning like single parameters, can we actually learn D itself, like the entire thing, the whole operator? Okay, so how are we going to do this? So we need to bring in a few ideas. So the first is we have to make some assumptions about the operator. We can't just learn something completely randomly. So let's assume a couple of things. Like first, we're going to say our differential operator. So this could be the wave equation, Berger's equation, harmonic oscillator, etc. We're going to assume that it's composed of like a bunch of operators. So like first order derivatives, second order derivatives with respect to our input coordinates. So, you know, given these operators, we could form like the wave equation, we could form the harmonic oscillator, Berger's equation with these things. And then we're going to assume that the operator can just be represented as this matrix here, lambda, times by these operators. Okay, so let's make that more concrete and like take the example of the harmonic oscillator. In that case, this lambda matrix here is just k, mu, and then the mass times by these things. And then we end up with what is our differential equation, essentially. Okay, cool. So then when we're doing pins for equation discovery, it's actually very similar to how we train it for the inverse problem. But instead of learning these like single parameters of the PDE, we're going to learn this entire lambda matrix here. So this whole matrix of possible coefficients of all these different operators. So I mean, I've restricted phi here to be a very small set, so that I basically just have the coefficients here. But you can imagine if phi is way bigger, for example, in like high dimensions of spaces, this could be a very large matrix. And it's also going to be a very sparse matrix. Like you can see some of the values where these coefficients aren't used are just going to be 0. And that's probably going to be true for a lot, if your library is very large. So phi in general is like a sparse matrix. But still, it's still a matrix of single coefficient values. And so what we do is, instead of learn these single values, we learn the whole matrix. And so we replace D here in our physics loss with phi times phi, the library of operators times by lambda here. And then we learn lambda. And in this and we have the same data loss as we had for the inverse problem. So in this sense, it's actually a very similar setup. We're just learning, you could think of it as learning all the coefficients of the PDE rather than just a single one of them. But as our whole discussion about ill-posedness of inverse problems, this becomes a massive problem because we're trying to learn the entire thing. And so these problems or this setup is generally very ill-posed. And so what we need to do is we need to put some kind of regularization or prior on lambda. Basically, what is our assumptions of what the differential equation could generally look like? And one assumption you could say is, okay, well, I think this should be sparse. Like, I don't think we should use all of these operators. I think this is just going to have a single key values in some of the operators. So, and the way that we enforce sparseness in like a loss function is we say, okay, the norm of this should be close to 0. Like the values should be basically 0 everywhere. Yeah, so I've put an L2 loss here, but you can have an L1 or an L0, depending on what norm you want. So, and you can have other, in a machine learning speed, this would be like a regularizing term. So you can add whatever you want. Yeah, go on. Stop. Yes. Well, yeah. Well, you could actually. So you can just change this. So you could have operators which are nonlinear. So you could have like u times by this, or this times by this, for example, and then like however you want, and it gets more and more expressive, but also harder and harder to learn. So there's like a playoff. So yeah, in theory, it's not limited. But you can imagine if you actually really want to solve this, you need a lot of data to like really understand the gradients. What you're really doing is you're fitting a neural network to a bunch of data, and you're using the neural network to get to evaluate gradients at those points, and then you're just doing a regression on those gradients to figure out what the differential equation is. That's really what's going on here. We're just doing this jointly. We're learning that we're fitting the network and doing the regression all at the same time. Okay, so there was a paper that came out very recently in Nature Communications, which is basically this exact idea that I just described to you. They added lots of bells and whistles to it as well, but it is basically what I just described. So you have a loss function where you're minimizing the network's prediction against some observational data. You have your physics loss, but inside the physics loss is this differential operator, which is flexible, which depends on this coefficients lambda. And then we add some regularization here. And yeah, you can think of learning the operator as like as a linear regression, and you can think of the training in DNN as like a standard neural network training. Yeah, and they actually do this alternating, so they update the lambda values and they update the weights of the network, and they alternate it between. Yeah, and so this is an example from that paper. So they're learning the Burger's equation, as you pointed out, and so inside that dictionary, they do have these cross terms. So this u times by du by t or whatever it is. And so they have examples of the solution of the Burger's equations for 3 different kind of boundary and initial conditions. And they're going to train the network to try and fit all of this data from these different conditions. And it's got some like Gaussian noise on it on top. And so, yeah, simultaneously, the PINN is learning the solution. So this is the like predicted solution for each of those different conditions, which looks like the Burger's equation that I showed you before. So it looks like it's converging nicely. But at the same time, it's also learning these coefficients of the differential equation. So this is showing, this plot here is showing each of those, the evolution of those coefficients as a function of training step. You see, so it starts off with this big dictionary of like many different possible operators. And then eventually at some point it decides those coefficients are 0, and it just takes a couple forwards. And those operators that it keeps, those coefficients that it keeps, turn out to be the ones that are the actual Burger's equation. So you can compare the equation that's the ground truth and the one that it kind of discovered in a sense from the data, and yeah, they match to pretty closely. So yeah, this is definitely not you know, discovering Einstein's equations, like actually figuring out relationships between like geometry and space, etc. But it is kind of what I like to think of it as like regression of gradients, and that does let you like discover some parts of differential equations. So it's kind of one step in that direction. Yeah, so that is everything from today. So I hope you enjoyed it, and look forward to seeing you next week. Yeah.